All right. Hope everyone can hear me. It looks like the microphone's working. Great. It's 9:15, and I'm here to do office hours. I've received a ton of questions beforehand, so I'm going to start to go through those. But for those of you who are on, and I can see there's a number of people already on, as you have questions, if you can chat in the chat window, you can ask a question there and I'll answer it. But if like that doesn't work or you don't want to do that or whatever, you're also welcome just to send me an email and I'll be checking my email as I go. So let's begin. So good luck to everyone tomorrow. First question about the format of the exam. To remind, I think everyone hopefully got Dr. Campbell's email earlier that the exam will be in two parts. The first part will be a group section where you work with a small group of people, and all of that will mostly be short answer type questions. And then once you turn that portion in, there will be a individual part, and that is a mix of multiple choice and a few short answer portion questions. So it's a mix kind of of those two things. Just make sure you give yourself enough time, finish the group part. I would say when I was putting together the answer key, keep things really short and concise. Don't worry about, having very long explanations. A few of the questions will ask you to explain your reasoning. You can do that with like just a short sentence. Don't worry about writing a giant paragraph. Try to be like short and concise. I think you'll be fine. Okay, so let's start answering some actual questions. Let's see. How does the moment of inertia relate to the figure skating example that I keep using? So remember that the moment of inertia, I'll just review it, tells us about the distribution of material within a terrestrial world, actually any world. And so if it's 0.4, it means that the moment of inertia is that the density of material is distributed uniformly. That could either mean that the world is made of the same stuff, like all rock, or it could mean that it's a mix of things, but that it's all distributed in the same way. If it's less than 0.4, then it means that the densest material is all sunk to the center. For example, you might have iron and a world made of iron and rock. And if the density or the moment of inertia, say, is like 0.3, you'd expect all of the iron to be at the center and rock to be on the outside. Now, how that relates to the figure skating is the way we actually know that about worlds is that we actually look at how easily they respond to changes in their rotation. And so just like the figure skater who, when they have material, when you have your hands way out, you spin slower. It's harder for you to spin. When you pull your hands in, you spin very fast. You've changed your moment of inertia. Here, you had mass distributed much further out. Here, you had a much lower moment of inertia. You had your mass concentrated towards your center. You had a lower moment of inertia. It was easier to spin. So it's just how we determine it, but don't worry about that for tomorrow. Okay, what was the evidence that Mars was initially made up of water? We didn't talk a lot about that, so I don't want to spend too much time on that. But basically, I briefly talked about that Mars, one of the things that the Opportunity rover found was evidence of rocks and minerals that can only be created in a water or aqueous environment. And that's the main evidence, although there's a lot of other pieces of evidence for Mars being once wet and warm. We also saw that Mars is right at the transition where it doesn't have quite enough gravity to hold on to water for its entire lifetime. When we talk about that, some of the atmosphere questions that will come up. So Mars is right at the boundary where for probably a few billion years, it can hold on to water. It has enough gravity and it's the right temperature that water can stay on the surface. But over time, what happens is the water molecules can escape via thermal escape, one of the atmospheric sinks that we talked about. We'll get to that in a later question. Okay. Is there a way to rationalize the different atmospheric compositions of Venus and Mars using what you've learned? So this was question someone asked me to go over. Yeah, so I mean, Mars and Venus both are super rich in carbon dioxide, right? And one of the things we spent the last couple classes talking about was, why are they all carbon dioxide? If outgassing of volcanoes and other material from under the surface of the world is giving you things like water and carbon dioxide and nitrogen and other things like that, why are Mars and Venus mostly still carbon dioxide? In both cases, it's probably because the water has been removed. In Venus, it's probably mostly due to solar wind stripping that actually got so hot that the water, and you actually had, it was already closer to the sun, so you had solar rays actually breaking apart the water molecules. In Mars case, it didn't have enough gravity to hold on to the water. There's no oxygen on either of those worlds because, at least as far as we know it, on Earth, most of the oxygen is caused from life. So that's why those are so different. And carbon dioxide is a very, very heavy molecule, at least as far as they, compared to many of the other molecules that come out of outgassing. And so it moves much slower at a given temperature than a much lighter molecule. And so it's much harder for it to like escape off a world. And so in that case, like it's the easiest molecule to hold on to. And so it's not surprising that it's a very common molecule on worlds, especially ones like Mars, which is it doesn't have very strong gravity, and on Venus, which is so hot that lots of things can escape via thermal escape. So I think that's the best way I can quickly rationalize it. Let's see. Next question. I'm doing these in the order they were sent to me. Much like the water cycle, Earth has a carbon dioxide cycle. Say you were a cave person back in 100,000 BC, all right? What are the main sources of carbon dioxide, and how is the carbon dioxide sequestered or gathered by the Earth? Okay, so if you were a cave person back in 100,000 BC, main source of carbon dioxide would still be mostly still from volcanism, from outgassing. So what happens is, volcanoes and other places in the Earth where there's hot vents, we didn't talk a lot about that, but let's say volcanoes are spitting out all sorts of gases. We know they're spitting out water on Earth, they're spitting out carbon dioxide, nitrogen, some other elements. That would be the main source. Of course, life like us, we breathe out carbon dioxide, so that's a little bit of a source of it. But back 100,000 years ago, we didn't, we didn't have cars and other things spitting out carbon dioxide. And then the other part of the question was, how is carbon sequestered? How is it gathered by the Earth? And so one of the things that has been happening 100,000 BC now is that the carbon can get broken down, but we saw that by chemical weathering. So you get lots of rain, the rain hits the rocks, there's a chemical reaction that actually occurs where the rocks actually absorb carbon dioxide, and then that carbon actually gets trapped in usually pieces of like calcium carbonate or other minerals that flow into the ocean. And then things like snails and stuff can actually use it. I think you'll talk about this more with Dr. Campbell. But then over time, whether those turn into just stay as minerals or turn into shells, they get trapped at the bottom of, say, the ocean. And then over time, the ocean plates get subducted under other continental plates. and that actually stores the carbon dioxide underground for a very long time, which it then later releases in outgassing. So it's this kind of constant process that's happening. That's one of the ways. Of course, on Earth, even even at 100,000 BC, there's a lot of life that actually also absorbs carbon dioxide, whether it be plants or plankton in the ocean. A lot of that, a lot of the carbon dioxide that's pulled out of the atmosphere actually comes from life as well. So that's the other answer to that. A related question: how has this equilibrium shifted in the last 250,000 years? 250 years. Predict the implications for an increase in CO2 in our atmosphere. So we talked a bit about this, that over the last 250, like I'm frozen. Okay, there we go. There's been a sharp increase in the CO2 in the atmosphere, and a resulting increase in the temperature, kind of out of the normal equilibrium that has been over the last actually many hundreds of thousands of years. This has been attributed to the rise of industry and the use of fossil fuels, which are pumping huge amounts of CO2 into the atmosphere and causing the greenhouse effect to be more effective. And of course, just to remind you, the greenhouse effect is where you put materials like water, CO2 into the atmosphere, and it doesn't let infrared light easily in or out. So what happens is, the sun shines on, the sun's mostly visible light. It reflects, it heats up the surface gets hot and emits actually mostly infrared light. And then that infrared light, if there's a lot of greenhouse gas, can't actually escape. In the Earth's case, some can still escape, but actually the more greenhouse gas you put in, the less of that kind of heat can escape, and it actually continues to heat the planet. Like in Venus's case, it's been a runaway greenhouse effect where it's just constantly heating because there's so much so much CO2 in the atmosphere that essentially no heat can escape. It's actually at the point now where almost no heat can get in because it's so cloudy and so much CO2 in the atmosphere, but it got there because you still could get some sunlight in and nothing could escape because the CO2 levels got so high. Next question: what is the evidence for plate tectonics and how does it affect Earth? What are the ages of rocks on the Earth? That's two questions. I'll do the first one. What is the evidence for plate tectonics and how does it affect the Earth? Well, evidence of plate tectonics was several different things. One was, of course, just the motions of the continents that we saw, and one of the there was a couple various lines of evidence. Whether it was continuations of mountain ranges, looking at the Appalachians, look like they continue off into even Scotland. That you had fossils on various continents being similar, climate that was drastically changed, that was drastically different in the fossil record than it currently was, indicating that possibly those continents that were, in the tropics were once in the Arctic and vice versa. But I think the main, I think the main piece of evidence that at least I talked about, and I think it was in preparing for this class, the strongest piece of evidence out there is the paleomagnetic evidence that actually showed, especially at the ocean spreading regions, where you have new rock that's being formed at these ocean centers, that you can actually see as the plates are moving away from each other, that you can actually look at the magnetic history of the Earth, and you can actually see that plates that rock of certain age matching certain magnetic patterns in the Earth's history, because the Earth is flipping its north pole from essentially the north of the planet to the south of the planet every so often. you can actually see that pattern in the newly established rocks. And that shows us that the rock is forming and then moving apart at a given rate. You can actually measure that rate in the magnetic imprint of the ocean floor rock. And I think that's the strongest piece of evidence for plate tectonics. Ages of rocks on Earth. Oldest rock is about 4 billion years, but most of the rocks are much less than 3 billion years. Ocean floor rocks are, millions of years old, very young, because again, that's where a lot of the new rock is being formed, is in the ocean. And then the reason the Earth, of course, doesn't have the oldest rocks that it would, the rocks that would be the age of the Earth, which is 4.567 billion years old, is because, of course, Earth has a lot of processes that are destroying rocks, whether it be subduction of continental plates, which destroys those rocks. It could be weathering, which we know is a process that destroys rocks. It could be other types of erosion, could be glaciation, all sorts of other things. There are other processes that destroy rocks, and it's the reason why there just aren't very many old rocks on the surface of the Earth. Let's see. Someone wanted me to go over the question of the day that was, how would all end? What's left to learn? How do we look for life beyond Earth? So that was the kind of last lecture. How will it all end? I guess what I really wanted you to take away from that, as depressing as it is that, the universe, billions of years from now, the universe is a very dark, cold place. All of the stars will essentially run out of gas. The galaxies will actually run out of gas for forming new stars. And the universe will have moved so far apart, or galaxies will have moved so far apart because of the universe's expansion, that we won't even be able to see other galaxies in the sky because it'll just be too far away. For the Earth and the sun itself, I do want you to know that that because the sun is constantly getting hotter, right? It's now 30% brighter than it was when the sun began. The sun is constantly getting brighter, and because of that, it will heat up the Earth's climate such that plate tectonics will stop. Eventually, it'll stop plate tectonics, which will really halt that carbon cycle. So it will actually lower the amount of carbon dioxide in the air, which, seems great for like greenhouse effect kind of stuff, except for it like kills all plant life. Like no longer can you have photosynthesis if you don't have carbon dioxide in the air. So you want a little bit of carbon dioxide for sure. And when there's no plant life, then all life dies on the planet. Eventually the sun gets hot enough to boil off all the oceans. And then, if that's not enough, somewhere between 5 to 7 billion years from now, the sun gets big enough to likely like enclose the Earth. And that's the end. So that's what I wanted you to know from that. Let's see. Another quick question. I understand infrared light cannot penetrate the atmosphere, but what type of light is unable to get out of the atmosphere once it is in? Visible light that contributes to the greenhouse effect. Oh, okay. So this is, I kind of just talked about this, but let me clarify. So it's really infrared light that is the key thing for the greenhouse effect. And it's that gases like carbon dioxide and water. I mean, water is actually like the strongest greenhouse gas, but we don't talk about it a lot because the one that like we talk about in the news and unfortunately in politics and stuff like that has been carbon dioxide. But water actually is like a much stronger greenhouse gas. But anyway, it's neither here nor there. Infrared is the important type of light. It's that the greenhouse gas blocks infrared light. So it blocks it from coming in, but it also blocks it from coming out. So, in the case of the Earth, most of the visible light from the sun comes into the surface. it heats up all the rocks and the ground and whatnot. And what re-radiates is mostly infrared light. Like you and I are emitting huge amounts of infrared light. We're warm, so we're giving off huge amounts of infrared light. Because of the greenhouse effect, then you've transferred, that visible light energy into now infrared light as it bounces off the Earth. And because you have greenhouse gas in the atmosphere, that infrared light, not all of it can get out, and it warms the planet. And the more greenhouse gas you have, the less of that escapes, and the warmer the planet gets. So that's kind of where I was going. Hopefully that makes sense. So, in the Earth's case, the visible light comes in, actually does the warming of the surface. Normally, without as much greenhouse gas, the infrared light would escape and the planet would cool. But that's not what happens currently. Let's see. What are secondary atmospheres? Why are secondary atmospheres not all the same as outgassing? So I think I touched on that a little bit. So like we saw in at least the three examples I gave, Mars, Venus, and Earth, that their current atmospheres, which are their secondary atmospheres, remember their primary atmospheres are like what the planets probably had at the very, very beginning. And those, the primary atmospheres are literally like what the sun is made of. So hydrogen, helium, and a little bit of everything else. But the Earth, for example, just didn't have enough gravity to hold on to hydrogen and helium. So those very quickly just went away into like space, into interplanetary space. And what was left was kind of everything else. And then, of course, via mostly outgassing, the Earth began to create its secondary atmosphere. But its secondary atmosphere doesn't look exactly like outgassing because of things like life, which introduces oxygen into the Earth's atmosphere, because of the carbon cycle, which takes carbon dioxide out of the atmosphere and then puts some back in, and so on and so forth. And so there are processes that are mostly that sink, that hold on to various elements. And there are processes that remove things entirely. We talked about the thermal escape. We talked about the solar wind stripping. And I'll spend a little bit of time with the thermal escape. I want to make sure some people had some questions about that. I want to show the specific graph. And I brought a whiteboard down so I can show you that. I want to get through a few of more of these questions. How does the Earth create and sustain its magnetic field, and how do we benefit from it? Great. So a lot of people had questions about magnetic fields. So let me give you the real basic physics. Magnetic field is generated anytime you have moving charge, like straight up. If you move charge, you make magnetic field. Like all of our computers or iPhones or whatever you're streaming this office hours on, right? They've got all this electronics moving through them. There's magnetic fields being created. That's just it's one of the principles of physics. We could have a cool, longer conversation about that. But in the case of planets and stars, actually, this is the same for stars. What you need is some conductive material that can kind of move around, that then becomes rotated. So in the case of a star or a planet, and it actually is one of my specialties is in magnetic fields in stars, but it's really similar to what you get in a planet, is you need a conductive material that can move around, and you need fast rotation. So you need two things at the base level. And so for the conductive material, for at least terrestrial planets, we think that you need a probably molten part of the core. So you need, because especially since most of the cores, if they're a differentiated world that has a moment of inertia, less than 0.4, you've moved all that material, which is mostly now going to be iron, down to the center. Iron is conductive, and if it can move around, if it's molten, now you can send current through it, and if it's rotating fast enough, generate a magnetic field. And we actually think that is the main way that Earth creates its magnetic field. So the two things then, again, if you need stuff moving around, you need fast rotation. Okay, so fast rotation is number one. If it's rotating slowly, it does not have a magnetic field. Venus is an awesome example. Venus, we think, has a molten iron outer core, probably very similar to the Earth's. But Venus is not rotating fast at all. It takes, hundreds of hours, or maybe even, I don't remember the exact rotation, but it's like essentially like rotating super slowly. So it has no magnetic field. Whereas the Earth rotates, one rotation every 24 hours, which is actually relatively fast. And so it generates a magnetic field. If it were rotating faster, the magnetic field would probably be stronger. The other thing that is key to having, that is that it has a molten outer core, which is probably still a product of the world being geologically active. So what I would look for, if I were you, for a world to be magnetic, to have a strong magnetic field, would be a world that's rotating quickly, that is geologically active. So that's my hint to you all watching. So that's the two things I think required for that you need to know for magnetic fields. Can you describe the processes that formed the Earth and the Moon? Okay, so we talked about the Earth really forming in the disk of what we call the solar nebula. So the sun collapsed, as a giant ball of gas. It as gravity pulled the sun and the material that will make the sun closer and closer, as gravity likes to do, things began to spin. And again, like the ice skater, as the mass got more concentrated, it spun faster. That actually spun out a nice disk, just like I had a Frisbee here earlier in all of my junk because I'm a ultimate player. So here's, Frisbee, it gets spun out in a nice Frisbee. And the Earth formed just in the middle of this disk in a very similar way, actually. Material collapsed and gravity pulled together small, like pebbles, probably, we think even first, like pebble-sized objects, and pebble-sized objects stuck together and made boulder-sized objects, which stuck together and eventually made up a planet-sized object after a while. The moon is a much kind of more interesting thing. We didn't spend a huge amount of time on it, but I think I did tell you that the best idea for how the moon is currently formed is a Mars-sized object, like a planet-sized object, actually hits the Earth, the early Earth, like within the first a couple 100 million years of it forming, maybe even 10 million years of it forming, and actually breaks a piece off, kind of becomes incorporated in the Earth, and then a piece breaks off that it's actually the moon. And there's lots of pieces of evidence for why that probably is the most, why it is the most likely scenario, and probably why it is the scenario. I think one of the most convincing ones is the moon is like a pretty large body that actually has no iron core. It is, very close to like a moment of inertia of 0.4, which is super rare for an object of its size. And the idea is that it is just a chunk of the Earth's mantle, like the outer part, the all rock part that broke off because of this giant impact, and then remelted and formed the moon. And so, it's very unusual to have that. It's also big compared to, but anyway, that's the really quick Earth Moon formation. Let's see. Does the outer core mantle create Earth's magnetic field? Yeah. So we think it's probably mostly not from the mantle, but the liquid outer core is probably responsible for what we call the magnetic dynamo producing the Earth's magnetic field, given the same scenario I just talked about. Blah, blah, blah. Difference between primary and secondary atmospheres, I mostly just answered that, but the follow-up to that is what kinds of planets have one or both or neither. So all of the terrestrial worlds we talked about that have significant atmospheres, Venus, Mars, Earth, Titan, which we didn't talk a lot about, but has a significant atmosphere, even though it's not a planet, it's a world, it's a moon of Saturn. All those are secondary atmospheres. Like the primary atmosphere, the hydrogen, the helium, all of that is like gone. And mostly because those worlds didn't have enough gravity to hold on to it. But planets like Jupiter, Saturn, the big worlds, Uranus, Neptune, those have their primary atmospheres. Those are the atmospheres they've had since like formation. And that's because those planets have enough gravity to hold on to what they held on to like when they were formed, and they have like continued to hold on to it. They also don't have volcanoes and shit like that because they're just big balls of gas. They have lots of other interesting things, but not the same kind of geology that we mostly talked about. None have both. One of the questions asked, like, do you have both? No, you're either have pretty much your primary atmosphere, or you got rid of your primary atmosphere and you have your secondary atmosphere. So the really big planets, primary atmosphere. The small terrestrial worlds all have their secondary atmospheres. How or when are rocks' ages reset? So we talked about this when we talked about how we radiometrically date rocks. Oh, it says chat is disconnected. Huh. I don't know why that is. Let me see if I can. Hey, look at that. There's now 1 million questions. Holy crap. All right, well, I'll go through these and then start going through those. All right. Wow, awesome. Okay, sorry. Rock ages reset. So we talked about this when we were talking about radiometrically dating objects. So we look at the radioactive isotopes, the radioactive materials in rocks. And from studying those and how many are left compared to actually other elements in the rocks, we can actually determine very precisely the age of the rock. But what happens is when the rock is remelted, so if you melt the rock back down, when the rock resolidifies and forms the crystals, it actually goes through this little chemical balance equation, just like you probably all did in chemistry. And it redistributes all of the amounts of the various elements in like a big chemical formula, and it essentially resets the age. So, if you had rubidium turning into strontium, which is actually one of the things we use in doing this process, if you let that rock go 4 billion years, a lot of the rubidium would be gone, and you'd have much more strontium. And you'd be able to actually calculate exactly how long that rock had been sitting there. But if you remelted that rock, now the rubidium amount would come back up to its original amount compared to the amount of strontium to match like the chemical formula, and boom, like the rock would look like it's 0. So once you melt the rocks, you reset them. All right, oof, wow, a lot more questions. We'll go, I'm going quick. We got half an hour, we got lots of time. Does the Earth's formation resemble the creation of stars, galaxies, the universe? If so, in what ways, if so? Well, I would say like star and galaxy formation is like really similar. I mean, that's where I'd actually put the most similarity, that like you have these big balls of gas that collapse under gravity, and then things start rotating and you form these disks. So you form a nice spiral galaxy in the case of galaxies. And from that gas and disk, you then get little pockets that form stars. And I guess it's self-similar in that, like, within that pocket of that disk around a star, you form planets. So I guess in that way, it is self-similar. And it's even more self-similar that, at least not in the case of Earth's moon, but like certainly Jupiter's moons and Saturn's moons, there's really good evidence that those were formed with like little disks around Jupiter and Saturn. And actually, they had their own condensation sequence, which we didn't talk about in this class, but it's actually kind of cool. But yeah, so in that way, I think it's self-similar. Hopefully that whoever asked that question, that gives you enough information. Let's see. What does the moment of inertia tell us about the composition of the planet? I think I went over that already, so I'm going to go over that. Can you explain how the Earth gets magnetic field? I already talked about that too. Okay, I'm going to go, before I go to talking more about atmospheric escape, I want to go to some more of the questions here. We understand the cosmic microwave background radiation is light left over from the Big Bang, but why does its presence in all directions so that the universe is expanding uniformly? Well, it doesn't actually by itself tell us that. Remember, the evidence that really the universe is expanding, that at least we talked about in this class, is that galaxies are moving away from us, and that the farther the galaxy is, the faster it's moving away, right? That is the piece of evidence that the universe is expanding uniformly. Now, it turns out that there are pieces of information in the cosmic microwave background that confirm that actually tell us something about the makeup of the universe, that confirms the expansion of the universe. But we did not talk about that in this class. What it does tell us is, why I think it's important is it's a major confirmation of the Big Bang Theory. So the cosmic microwave background was predicted by the Big Bang Theory. Like, no one knew about it, right? But they came up with this giant theory of how the universe formed. And in that theory, there were a bunch of predictable observations, right? This is like the way you should do any great scientific theory, is you should say, here's what I think happens. And if this is true, here's like 6 things that we're going to find. Okay. And like the cosmic microwave background was one of those for the Big Bang Theory. And, if any one of those predictions fails, the whole theory fails, right? And we're at a point now where none of the Big Bang Theory predictions has actually been disproven. Right? You can't prove anything in science, but you can disprove things, and that hasn't happened to the Big Bang Theory. It doesn't mean that every single thing has actually been found yet. There's this thing called the cosmic neutrino background that the Big Bang predicts, that no one's found yet, probably because we don't have the technology to do it. If you found it, you win the Nobel Prize, like guaranteed. Like if you want like one thing you will win the Nobel Prize for, it's to find the cosmic neutrino background. But that's the question that I got here, is that we didn't talk about the Big Bang as a piece of evidence for expansion. We talked about the receding galaxies farther away, moving faster, was evidence. Okay, could you talk about question 1? I already did that one. The why our secondary atmosphere is not the same as outgassing. I already talked about that. Okay. Besides telling us the age of the galaxy and showing us how it's moving away, how do stars inform our study of galaxies? That was, I think, one of the questions of the day. And what I really want to do to get there is I think I had you guys in class even look at pictures of galaxies, and based on just the little tiny bit you knew about stars and the different types of stars and stellar evolution, you could look at a galaxy, and if it was blue, you knew it had to be made of blue stars, which are really young stars. So I was trying to get you to think about that, by just looking at some really basic properties, like the colors of galaxies, which are really the stars in the galaxies, it can actually inform you about the galaxies themselves. So if you see a really blue galaxy, you know that it's a galaxy that's undergoing really current star formation because it has a bunch of young stars in it. That's what I was trying to get you to kind of think about, that these things in astronomy are very connected. You study stars, but stars make up galaxies. So the more you know about stars, the more you know about galaxies, which hopefully makes sense. But I wanted to show you that there were some simple examples of how you could do that. Let's see, we talked about the different atmospheric compositions, talked about secondary. Also, is there a key to the questions? Oh, I don't think there's a key question, but I'm happy to answer like any questions to the geology things. Those are actually I didn't write. I wrote most of the exam you guys are going to take tomorrow, but those were actually written by like the TAs and Dr. Campbell, and some of them are like from old exams from this class previously. So most of them are highly relevant to things that we talked about or that you might see on the exam. But actually, a couple aren't because we just didn't talk about them. We talked about using moment of inertia. How do we gather info on the properties of exoplanets? Does an exoplanet's velocity tell us about its mass? Oh, good, like couple good points there. So we talked about two main ways to identify exoplanets. One was the radial velocity method, and that's when you actually look at the velocity of the star. You do not observe the exoplanet. You watch the star as it wobbles towards you and away from you. Remember, that's that like thing that I told you you were like lied to like your whole life, that the sun isn't actually stationary, that it's like moving in response to the rest of the planets. And what we actually observe is the star itself kind of move towards us or away from us in response to having an orbiting planet around it. And it tells us about the mass is the question. It tells us actually about when you look at the orbit of that star from its velocity, it tells you about the distance that the star is away from you, and then actually you use that distance along with the amount of wobble to tell you the mass. So from that, we get the mass. If you also get a transit of the exoplanet, so this is the method where you have a star and the planet passes in front of the star and dims the star a little bit, that tells us about the size of the planet. Okay, so those two methods give you either a size or a mass. If you can use both of them, right? So there are a set of exoplanets that we've measured both their transits and their radial velocities, so that we get both a mass and a size. Then we can calculate a density of those worlds, and you guys could tell me what those worlds are made of, right? Like if they have a density of 5 grams per cubic centimeter, it probably means there's some combination of iron and rock, right? And we have exact exoplanet examples that are like that. So that's really what I wanted you to know, that like you can actually get some pretty cool properties from these exoplanets without actually even seeing them, right? Just looking at the stars that they're orbiting, you can actually tell what they're made of, which is pretty cool. You can also, we briefly talked about measuring the atmosphere of exoplanets, and that is a direct measure of their atmosphere, and that's by actually taking a spectrum of the exoplanet when it's in front of the star. This is if it's a transiting exoplanet. And there you're taking a spectrum of the star plus the atmosphere of the exoplanet. And then you take one of just the star and you subtract the star and you're left with the exoplanet. So we do have a few examples of the atmospheres of exoplanets using that method. So I guess that's another one. Okay. Let's see. Someone asks, is the reason the moon stabilizing the Earth's rotation is important is because the stabilization of the Earth makes the climate more irregular? Yes. Answer correct. So the moon stabilizes the axial tilt of the Earth, which actually keeps our climate more stable. The tilt actually still does wobble a little bit. And that actually, even that tiny wobble of a few degrees actually does actually have an effect on the Earth's like long-term climate. But without the moon, that would be much bigger, and the Earth would have much larger climate swings than it does. Someone asks, major forces driving the carbon cycle. I think we talked about that. Plate tectonics, life, weathering. I think those are the major ones. Right now, humans. What are the main ideas we need to know in the astronomy section? That's a pretty broad question. It's a good question, but it's a broad one. I mean, I would say like any of the questions of the day. This is true for like the whole exam tomorrow. Like when I was sat down to write the exam, I actually went through all the questions of the day. I pulled up all of those slides, and I was like, okay, what did I expect they know? And it doesn't mean I'm going to ask you like the question of the day verbatim. I'm going to come up sometimes with some clever way of like making sure you knew what the question of the day meant. But if you wanted to know what things are important in the astronomy section, go through and read the questions of the day. I don't think there's any problems. There certainly are no questions on the exam that aren't related strongly to the questions of the day. So let's see. When we know that the universe is expanding uniformly, and the evidence for that is, again, looking at galaxies, farther away they are, the faster they move. These galaxies with known light properties were observed as redshifted, and thus it was concluded that galaxies were moving away from us due to the Doppler effect. Known light properties. I'm not sure where that quote comes from, but I assume that means, these were galaxies. I think that probably means that the way that we actually do this is by taking a spectrum of the galaxy, and we look at those spectral features. So those are like the known light properties. Oxygen is always at this wavelength. Hydrogen is always at this wavelength. So if you see those shifted just a little bit, that object, whether it be a galaxy or a star, is moving away from you if those features are shifted to the red, or towards you if they're shifted towards the blue. Okay, magnetic fields. Oh, what's required for a planet to be habitable? Goldilocks zone, water, anything else? I mean, at this point, we don't really know the answer to that. I would say, like, for us to really call it habitable, and we do call planets habitable, or at least in the habitable zone. It doesn't mean they're actually inhabited. It means they're habitable. Yeah, they need to have liquid water. So not just water, but like liquid water on the surface. So they have to be in the right temperature range, that they aren't going to have, it's not all going to be frozen, and it's not all going to like boil away. And yeah, they have to have the right temperature then, of course, and they have to be terrestrial, right? They can't be a like giant Jupiter-sized planet. You could argue magnetic field is important, but we don't really know if that's important for life. It is for you and me, but it may or may not be. Let's see. There's a couple questions from like the homework. Let's see. It says you discover a planet with a mass 2 times that of Jupiter's orbiting a nearby star. Planet orbits the star at a distance of 1 AU. Must observe 3 transits. Yeah. How long do you have to wait for it to observe? So this was from the homework. So the idea there, of course, was that you have a star that's exactly like the sun. You have a planet at 1 AU, so it must take 1 year to go around, right? Planet's mass doesn't actually matter unless it becomes an appreciable fraction of the stars. So for all real planets, the star's mass is going to dominate, and then it doesn't matter what mass is. Any object at 1 AU is going to take 1 year to go around a solar mass star. That's the key thing I wanted you to actually see there. Let's see. Why does Earth's atmosphere have so much nitrogen? So it actually is it's like the product of the outgassing. Like nitrogen is one of the outgassing things, and it turns out there's not a major sink for nitrogen. That's an awesome question. Who asked that? Camille. Oh, Camille, of course, asked that. Yeah. So it's that, like, it's one of the like minor products of outgassing, but nitrogen is actually kind of massive. It's like not as light as like hydrogen or helium, but it's certainly not as heavy as carbon dioxide. But there's no major sink, right? Like it's not like something like oxygen, gets used by plant life, by a lot like large biological life like us, right? Nitrogen, we breathe it in, we breathe it out. Like it doesn't get used by a whole lot. So there's no major sink. There is some solar wind stripping, as you talk about. There a little bit might leave via thermal escape, but again, like most of it doesn't. And so basically it's like the one product of outgassing that just kind of keeps going. Let's see. Oh, some of you guys are answering each other's questions, which is awesome. Magnetic field does protect from solar wind stripping. It does, in fact. Yeah, so the magnetic field protects us from some of the like charged particles coming from the sun. Not only does it prevent those from like come raining down on Earth and giving us all sorts of crazy cancers, but it also does protect the upper atmosphere. There is some ultraviolet light that can cause solar wind stripping, and that's not protected much by the magnetic field. But the actual charged particles doing the damage, those are prevented from getting too far in the atmosphere by the magnetic field. Wow, so many awesome questions. Let me see. I want to make sure I get time to do. Let's see. There's one that's related to that. Is the UV dissociation of water solar stripping? That is one form of solar stripping. It's the most common one that we talked about. That like you have a water molecule, either a UV photon, or in this case, it could be a charged particle, breaks water apart. You now have oxygen, hydrogen. Hydrogen's really light, it leaves. Oxygen stays, combines with something else, and that would be the stripping. Sorry, I'm just not gonna have time to go to there's like a million questions, which is so awesome, you guys. Is there a correlation between the planet's past and the frost line and their moment of inertia? No, moment of inertia, like basically like if a world is differentiated, then usually it has a moment of inertia less than 0.4. So, and remember, differentiation is when the planets, it's one of those steps of terrestrial planet formation. And that's usually like happens really early. And when that happens, all the dense stuff sinks to the center, and now you have a moment of inertia less than 0.4. So, with the exception of a world like the moon, which is, again, I said it was weird, most worlds that have moment of inertia factors of like 0.4 are worlds that are not differentiated. So there actually may be a mix of iron and rock and ice, but it's like spread evenly around the world, the world. Most of those worlds are really small. So usually once you get to be actually a little bit smaller than moon size, you differentiate. We didn't talk about that in detail. And that's, remember, why you have like these asteroids that look like potatoes object, like, like big potatoes rather than nice like round balls. Those worlds are not differentiated. Those all have like moment of inertia factors of 0.4. But again, I don't really care that you know that. Let's see. How do we study evolution when the timescales are so long? Oh, that was a cool question of the day. So the idea there was I was trying to get you to think about, that fact that astronomy is this like ultimate in time, that, every, farther we look away, the farther back in time we look. So, takes our galaxy 200 million years to actually make one orbit, right? For our sun to orbit one time around the galaxy. Like that's how fast the galaxy is rotating. It's rotating pretty fast, but still the distances are so vast, it takes a long time. We're never going to see change, right, in a single object. But what we can do is look a little farther away at a similar type galaxy. We can see what it looked like, a billion years ago. And that gives us some information, especially when we do it statistically with hundreds, thousands, now even millions of objects. We can actually look back in time and see how things changed by looking farther away. Let's see. How do we know evolution timescale? When you answer each question, could you please say how important it is for us to know tomorrow? I think I've already actually done that if you were paying attention. Why will plate tectonics stop when the sun becomes hotter? That actually has to do with water. So when the sun gets so hot, it actually begins to evaporate all the water. And the oceans begin to evaporate. But first, actually, it pulls a lot. The water gets outgassed. It actually gets you get much more clouds. The water actually gets pulled, preferentially removed from underground, and the plate tectonics actually are able to move because they're on kind of a layer of at least hydrated rock, like the water in the rock and at the kind of boundary of the mantle lithosphere there is very water rich, and we think that's a main reason why you're allowed to why the Earth can actually move these big plates. So once you remove the water, we think plate tectonics stops. Evidence for water on Earth coming with comets versus not. Well, so we didn't actually talk about it from comets. So the evidence is actually, this is where the astronomer in me wants to slap upside a lot of the geologists out there who are like, no, it's not from comets. Well, it isn't from comets. It's probably from asteroids. People have looked at they looked at the specific chemical compositions of things like comets and the water on Earth, and people have said, it doesn't look like they match. It can't be from comets. Well, it probably is from, most of the water is probably, again, almost certain, you cannot have water formed at the location of the Earth. It's just too hot when the Earth formed at about 1 AU. All the water would be vapor. You would not have built a terrestrial world with any water on it. It's just too hot. Would have all boiled away and shot away. So you have to have some way of it delivering it from the outer solar system, and not way out. Actually, probably most of the water came from the outer asteroid belt. So not comets way out beyond Neptune, or around Neptune, but stuff between Mars and Jupiter, which much of which is actually pretty water rich. And again, the simulations show that it's very easy to take material from there, which has a very similar chemical composition in its water to that which we have on Earth. And it's very easy to do that. So, but I think that's key to remember that. Again, it's key to remember that you really can't have water form on a planet at Earth's distance, even though it's vital to our life and all life. That you actually have to bring it in from farther away. Let's answer a couple of these. Let's see. Someone asked the red and yellow parts of the solar radiation spectrum. I don't have it right here, but if you have that up or you have the slide, the yellow part was the actual radiation the sun is producing. The red is what we actually see. And what I was hoping to show you there was the various places where no light gets through because of water or carbon dioxide in the atmosphere. And that's actually for me the best graphical representation of the greenhouse effect. Those are all places in the infrared where there are chemicals in the Earth's atmosphere that are blocking radiation from the sun, right, from coming in, but it also blocks it from going out. Okay. One last thing I want to do. Oh, let's see. Camille has one more question. No, awesome. Okay. Some of you still. The last thing I want to do, because a few different people wrote this to me, and I'll go a couple minutes over, is first of all, let me apologize. I probably can't get to every single person's questions. You guys had amazing questions. If there's anything I didn't get to, send me an email. I'm probably going to go to bed soon because I have a 2-year-old who gets up at 5:30. But I will write you a question. Definitely, I'll answer your question in the morning, certainly well before you take the exam. But I do want to do review this velocity temperature plot, because a number of people asked me to go over this, and you guys had so many questions we didn't get to it, but I'll go a few minutes over because I want to talk about this. So this was when we talked about atmospheres. This was the question of thermal escape. And so the main plot is a plot of temperature on the x-axis with velocity, and I had a bunch of gases on here that were a nice diagonal, something like this. Pardon my drawing skills, right? And they were at different heights. So let's make this one hydrogen. Sorry, this one oxygen, and this one carbon dioxide. Okay, so the top one is hydrogen, oxygen, carbon dioxide, and this is this is a couple of things, right? One, you can see that the hotter you are, the faster they're moving, because this is the speed the gas is moving, and this is the temperature that the planet is in this case. And so the whole course, I think I kept reminding you that all temperature is a measure of motion, and this is just a graphical representation of that, with the caveat that a lighter gas, so in this case hydrogen is the lightest molecular gas. Carbon dioxide, at least in the planetary sense, is one of the heaviest. So it moves slower at a given temperature than hydrogen does. It's much easier to move a lighter thing. You guys all know that. Right? You can push over a empty glass much easier than a full glass, right? Something like that. So so hopefully this makes sense to people. If you're hotter, you're going faster. So the more challenging thing I added to it was I added planets. And when I'm adding a planet, I'm adding, of course, the temperature of the planet. Let's put planet, A up here. Okay. So the x-axis is however hot the planet is. The velocity in this case is the escape velocity. So it's the velocity. It's how fast would I have to throw something off the surface of the planet for it to escape gravity. Okay. So there's the complicated part about this plot is the velocity. If it's referring to the gas, is just how fast the gas is moving. If it's referring to the planet, it's the escape velocity. If I were to put another planet, down here, we'll call this planet B, and we'll put one way out here as planet C. Okay, so I've got 3 planets. Planet A is way up here. It has a very high escape velocity, which means it takes a very fast speed or velocity to get off its surface or get out of its gravitational pull. So for a planet like this, all of these gases are moving slower than this planet's escape velocity. So this planet can hold on to hydrogen, it could hold on to oxygen, it could hold on to carbon dioxide because its escape velocity is so high. None of these gases are moving fast enough to get out of the gravity of this planet. So something like Jupiter is a planet like this. Saturn is a planet like this, right? Their gravity is so great that they can hold on to hydrogen. Something like planet B now, right? So B has an escape velocity that's down here. So, for example, oxygen is moving faster at this temperature than the escape velocity of B, as is hydrogen, but carbon dioxide is moving slower. So planet B could hold on to carbon dioxide because carbon dioxide is moving slower than the escape velocity of B, but the oxygen on planet B would just shoot right off, right? It's moving faster than the gravity can hold on to. Same with hydrogen by a long shot. So in planet B's case, it could hold on to carbon dioxide, but not oxygen or hydrogen. Planet C, of course, here is down here, and it has a very small escape velocity, right? So what that means, if you think about that, just the English in that, the planet C, it takes very little velocity to escape planet C. So you can see all of these gases, carbon dioxide, oxygen, and hydrogen, are all moving so fast they could easily just jump right off planet C. And planet C in this case could not hold on to any of these gases. So, if you had some question like this, planet A could hold on to all these gases and likely has a very thick atmosphere. Planet B can hold on to at least carbon dioxide, but it could not hold on to the other two for any appreciable amount of time. And planet C couldn't hold on to anything. This is like where the moon would be, although the moon is not that hot. All right. Hopefully that makes sense and that's clear, right? Like you're plotting temperature always, which is either the temperature of the gas or the temperature of the world. The velocity is either just the speed of the gas, in this case, really the average speed of the gas, or the escape velocity of the world, how much it would take, how much speed it would take to actually shoot off all the way off the world and not have something fall down. I don't know if there's any. I'm happy to stay just another minute. If there's any last minute questions, or I know I didn't get to every single person's questions, but hopefully I got to enough. I would say biggest thing, look over questions of the day. Rewatch this. There were some good hints in this. I don't know. Anything else for anyone else? There's still a bunch of you online. Anyone else have anything else? Trying to see if there's any other last questions. Oh, well, we have to memorize conversion factors. No conversion factors. Nope. The only things I think you really have to memorize are the 3 or 4 densities. Rock is 3 grams per cubic centimeter. Iron is, just under 8 grams per cubic centimeter. Water is 1. I kind of want you to know ice is a little less than 1, but what's the difference between stellar evolution and end stages? Those are one's a piece of the other. So stellar evolution is like the entire stage of the entire process of a star's life, from formation to life to the end. The end stages are just the end part of the star. So, I would include a star being on the main sequence, which is its normal life, as part of its evolution. But the end would be when it, turns into a red giant and a planetary nebula and a white dwarf, or if it's bigger, a supernova and a neutron star, or maybe a black hole. Let's see, another quick question. Let's see, what is the evidence that Mars was initially made up of water? I'm just gonna say, Jocelyn, don't worry about that one. It's really that we found rocks with the rover, that certain minerals that at least on Earth can only be made in a water-rich or aqueous environment. But don't worry about that for tomorrow. Any last things? All right. Well, I think if I don't see any in the next minute here, I will say so long. Good luck to all you guys tomorrow, and just take your time, have fun, and let me know if you have any other questions throughout the semester. I'm happy to keep answering questions, even though you'll have various other instructors. Oh, what are the most important things we need to study? Questions of the day, I think, are really again, I think you should, if you can have a quick couple sentence or few sentence conversation about most of the questions of the day with your roommate who's not in this class, you should be pretty set. Make sure you can do the velocity temp graph, the physiological benefit. Make sure you can do all the homework stuff that we did, especially astronomy homework. I think that will be pretty good. Physiological benefit of the Earth's magnetic field. Basically, the sun has a lot of high energy particles that get shot off into space in actually what's called the solar wind, and those would be super harmful to humans. They would actually cause all sorts of cancers and shit. They're they're like moving very fast, and some of them are actually very massive particles. So as they entered our bodies, they would disrupt our cells and probably give us all sorts of cancers. Not probably, they would certainly give us all sorts of cancers. So the magnetic field actually acts as a shield, and it actually traps all those charged particles in the magnetic field and doesn't allow them to get down to the surface of the Earth. So it protects us, which is good. All right, I'm going to sign off. Good night to you guys. Happy studying for those who are going to stay up and study, and good luck tomorrow. All right, let me know if you have any last questions. You can shoot me an email. All right, bye.